Okay, so autonomous equations, slope fields, and phase lines. So we'll talk about what is an autonomous equation, what does the slope field of autonomous equation look like, what are equilibria, and what are phase lines. So first off, an autonomous equation is one that doesn't involve the independent variable, and the independent variable here is t explicitly. So this differential equation is called the logistic equation. There's no t on the right-hand side, it's just y. And this one also has just y. And these kinds of equations are separable, right? Because you can move all the y's to the left side, but integrating them can be a pain, and we'll see exactly how in a bit. So what does the slope field of autonomous equation look like? Well, the right side of the equation depends only on y. The slope field is going to end up having a left-right invariance. So here's dy dt equals 3y times 1 minus y over 50. What's the slope field look like, and what do the solution curves look like? So I'm going to put up a little chart, a little table, y dy dt, right? And if y is 0, then 3 times 0 is 0. And if y is 50, then dy dt is also 0, right? Because if we put 50 in for y, we get a 0 there. What are some other numbers that could be useful? If y is 25, plugging that into the right hand, we get 75 times 1 minus 25 over 50, which is 37.5. If we plug in, say, 100, that's another number that's easily divisible by 50. We get 100 over 50 up here, and 100 over 50 is 2, so 1 minus 2 is minus 1 times 300, so minus 300. And suppose we plug in minus 50. If we plug in minus 50, we get minus 50 over 50 is minus 1, but 1 minus minus 1 is minus 1 minus minus 1 is 2. And then 3 times minus 50 times 2 is minus 300. So we've got some numbers, and so we can draw a slope field. How do we draw a slope field? Our axes are t and y. And everywhere along the line y equals 0, we draw in horizontal tangent lines. Now y equals 0 is the t-axis, so we put in horizontal tangent lines here. All along the line y equals 50, we'll put the line y equals 50 up here. So we get horizontal tangent lines all along the lines y equals 50 and y equals 0. Along the line y equals 25, right? And that's in here somewhere. So this is the line y equals 25. Those aren't slope fields because the slope is 37.5 there. So it means all along this line, we draw pretty steep slopes because 37.5 is pretty steep. Blah, 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 lots and lots and lots of vertical lines. At 100, which will be up here somewhere, so here's the line y equals 100. We have very steep negative slopes. I won't draw quite so many because its slope is minus 300. And likewise down at y equals minus 50 on this horizontal line, right? So these are all horizontal lines. We have negative 300. And there's our slope field. And so if you pick a horizontal line, you always get the same slope all along that horizontal line. So if we start at 0, 0, what's the solution curve that runs through there? Well, that's just the t-axis, right? There's a line that runs through 0, 0 that's tangent to all the solution curves. Likewise, y equals 50, the line that's tangent to all those is just that horizontal line. Now for y equals 100 to 50, right, there's only 2 zeros, y equals 0 and y equals 50. So you can't change sign if you go above y equals 50. If you take any number bigger than 50 and plug it into the right-hand side, you get a negative number. But if you take numbers close to 50, you actually get numbers close to 0. So we'll get shallow slope marks here. Same thing here, in between 50 and 0, your slopes are always positive, but if you're close to 50, your slopes are pretty shallow. Because if you take, say, 49.99 and you plug it in for 50, this term will be very close to 0. And we're also very close to 0 here, because if you take y equal to, say, 0.01 and you plug it in there, you're starting out with 3 times 0.01. And likewise, these are shallow. So near these horizontal lines that are solutions, you have pretty shallow lines. So what does a solution curve look like? Well, if I start here, come down, you can't cross that horizontal line, so you just have to approach it. Always going down though, right? We're always decreasing. In between 0 and 50, the derivative is always positive. That means our function is always increasing, but we can't cross the line y equals 50. So we come to a limit there, and we come to a limit there. And then these ones come out and down. And so there's our slope field with a couple of solutions in there. What can we say about the solution curves? Well, up here, y prime is 0. So what does that tell me about solution curves? They're decreasing. And the limit as t goes to infinity of a solution curve is 50, right? So the solution curve comes down here and comes asymptotic to that. In between here, y prime is greater than 0. So positive derivative means that you're increasing. And we actually have two limits now. Limit as t goes to infinity of y is 50. Limit as t goes to minus infinity of y is 0. Right? So if you pick any curve in here, in forward time, it ends up asymptotic to y equals 50, and in backwards time, it ends up asymptotic to 0. And for this part, y is less than 0, you have y prime is less than 0. What does that tell you? Again, it tells you that your solutions are decreasing. It tells you that the limit as t goes to minus infinity of y is equal to 0. In backwards time, your curve is going to end up asymptotic to 0. We don't know what's going on in forward time. So just as a point here, if y prime is greater than, if y is greater than 50, right, our solution curve looks like this, right? And it's asymptotic to the line y equals 50. So we know the domain of this curve is going to go out to plus infinity. What we don't know is how far it goes to the left. Maybe it goes all the way out to minus infinity. Maybe it's got a vertical asymptote. We just don't know at this point. And the same thing then also for y less than 50. Your domain is defined all the way to minus infinity, but we don't know whether or not there's a vertical asymptote or something happening for going forward in time. And note that these solution curves are all, if you move them left and right, you get the same curve, right? Because we're just meeting them at different times. So autonomous vector fields, unlike the ones that you see for calculus, have a left-right symmetry. Okay. So sometimes we can also have different equations given by a function. Here's some function given by a graph. Here's some function. This is y on the horizontal axis, and this is y prime, which is your derivative on the vertical axis, and that's y prime equals f of y. So how do we read this? Well, we know at 1, when y equals 1, y prime equals 0. When y equals 0, y prime is equal to 0. If y is between 0 and 1, y prime is less than 0, right? So if we're taking any y in this interval here, our y prime is negative because it's below the y-axis. If we take y less than 0, y prime is also less than 0. It's out here. We take y greater than 1, and my derivative is positive. Right? And that allows us to sort of quickly sketch a graph. What we saw in the previous example was any place where y prime equals 0, right? That means this horizontal line, y equals 1, and this horizontal line, y equals 0, they're both going to be solution curves. Why is that? Well, if we put in t and y and draw the slope field, the line y equals 1 is just horizontal slopes, as is the line y equals 0. I wish I could actually do that accurately. There we go. So what's the solution curve that starts on the line y equals 1? Well, you follow the tangent lines and stay tangent to them. Great. In between the two, right, y prime is negative. So I'm not going to draw it particularly out because it takes forever. But we know that near y equals 1, they'll be shallow. Near y equals 0, they'll be shallow. In between, they'll be steeper. If we're bigger than 1, we have a positive derivative. So that means we must have positive slopes. We have an increasing solution. If we're less than 0, we have a negative slope. And you can check all these things by looking on GeoGebra if you want. So what's the solution curve look like this? It's got to keep getting steeper up this way and go back that way. These curves, if we start here in between 0 and 1, slopes are negative, so it's a decreasing function, but it can't cross the y equals 0 line. It goes back. And same thing for this. Something like that. Right? So we can draw the slope field. What we're really interested in mostly in looking at autonomous vector fields is where is the slope 0 and what is the sign in between those y values. Okay, and what can you say about the solutions? Not much. This one's increasing, defined for all time in negative and backwards time, and it approaches y equals 1 in backwards time. We don't know what the domain is going forward. In between y equals 1 and y equals 0, the solutions exist for all time because they're asymptotic in backwards time to y equals 1 and asymptotic in forward times to y equals 0. And this case is sort of similar to this case. Okay, so we see a few things in these examples. On each horizontal line, the slopes are always the same, right? And what that is saying is that if I pick a line, which we did up here, right? Like y equals 25, here's a horizontal line, y equals 25. All along that line, you have exactly the same slope because your dy dt depends only on y and not on t. And that's what gives it a left-right symmetry. When dy dt equals 0, the slope field has horizontal lines, horizontal tangent lines. And the solution curve is that particular horizontal line, right? So we always look for these sorts of things. And if you have solution curves that are not horizontal, they either run towards or away from the horizontal solution curves, right? They have limits in forward or backward time that are the horizontal solution curves. And so those horizontal solution curves are really important, obviously, and those are what are called an equilibrium. Right? So for any solution to any differential equation that's just a constant solution, that's called an equilibrium. For these particular ones, dy dt equals f of y, any solution of f of y equals 0 is an equilibrium. And we can classify them. If solution curves run towards the equilibrium on both sides, it's stable. If they run away from the equilibrium on both sides, it's unstable or a source. Anything else is called a node. So what's this slope field for dy dt equals y sine y, and classify all the equilibrium? So So the first thing to do is find all equilibria, and we do that by solving y sine y equals 0. So either y equals 0 or sine y equals 0. And this last case is y equals n pi, where n is some integer, whatever integer you want. So pi, 2 pi, 3 pi, 4 pi, 5 pi, right? So I want to just verify, don't really need to do this, but I want to verify that y of t equals pi is a solution. And how do you do that? Well, you take your y's in your differential equation and you replace them with pi and see what you get. So left-hand side, we'll replace this y by pi. The derivative constant is 0. Right-hand side, we get pi times sine of pi, and the sine of pi is 0. So left-hand side equals right-hand side, it's a solution. So good, so the equilibrium solutions are in fact solutions. So this gives us a way to get started on what this looks like. Our slope field has axis t and y. T equals 0, y equals 0 is an equilibrium. So that means the t-axis. Y equals pi is an equilibrium. So it's a solution that's a horizontal line, y equals 0. Y equals 2 pi. And then we can have more other solution curves. So I'm just drawing in the solution curves rather than drawing on all the possible little tangent lines that you'd want to see on a slope field. Great. So what we want to know now is what's the slopes in between here, right? And it's y sine y. So if we take numbers in here, y is positive because it's between 2 pi and 2 pi, but sine y is negative because y is between pi and 2 pi. So y prime is actually negative. So we're having negative slopes in here. Between 0 and pi, y is positive and sine y is positive. So in between these two, we have positive slopes. Something like this. Now between minus pi and 0, y is negative because it's between minus pi and 0. And sine of y is also negative because we're down in the third and fourth quadrants. So a negative times a negative actually gives me a positive there. And so we'll have positive slopes here. Y between minus 2 pi and minus pi, that makes y negative, but it makes sine positive. So in here, y prime is less than 0. Now we can sketch some solutions. Anything that starts in between pi and 2 pi, in forward time is going to approach pi, and in backward time is going to approach 2 pi. Anything that starts between 0 and pi, y, right, is in forwards time going to go up, and in backwards time going to go down, right? So negative derivative means decreasing, positive derivative means increasing, positive derivative means increasing. So this one is also like this. Y prime less than 0 means we're decreasing. And you can extend this as far as you want, right? Because every pi you go, you're going to get a new equilibrium. So this equilibrium, y equals pi, it's got all the solutions are running towards it. And so that makes it a sink or stable. Y equals minus pi, as we go in forward time, everything is running away from it. So this is a source or unstable. y equals 0. On one side, things are coming towards it. On the other side, things are running away from it. So it's not a sink and it's not a source. Y prime equals 0 is what's called a node. And then 2 pi, well, everything on this side is actually going out this way. So this is actually a source. And everything here is going in, and this will actually be a sink. So we can classify our equilibria as sources and sinks. Okay, so when we're sketching slope fields for autonomous equations, we're really just looking at where are the equilibria, and there you get a bunch of horizontal lines, and then what's the sign in between the equilibria, is it positive or negative? So what we can do with autonomous equations, right, since we're really not so much interested in all the details, we're really just interested in what the where the equilibria are and what the sign of the derivative is, we can do something called a phase line. Right? So we'll draw the phase lines for this. This is the first example that we did above. This was the third example. So for example 1, dy dt equals 3y y minus 50. Our slope field looked like this. This is y equals 50. This is y equals 0. That was the other equilibrium. And everything up here was coming down. Everything in here is going up like this. And everything here is going down. So up here we have y prime is less than 0, y prime is greater than 0. In between the equilibrium, y prime is less than 0 outside of the equilibrium. So we can draw a phase line, which is just y, just the axis y. It's really just this axis. Put in a dot for y equals 0, put in a dot for y equals 50. Those are my two equilibria. In between, y prime is positive, so we put little arrows going up. Above y equals 50, the derivative is negative. Here, the derivative is negative. So this is a source or unstable equilibrium. Everything is running away from it. And this is a sink or a stable equilibrium. Everything is running in towards it, right? Things are sinking into here. They're starting out from there. So this is the phase line, right? And it encapsulates this entire thing. And note that every solution curve up here looks pretty much the same. In fact, it is the same, right? There's a right-left symmetry. And so rather than drawing out each separate one as it depends on t, right, we're just going to say, well, they're all doing this. And so this vertical line here encapsulates all of these sort of compressed onto one dimension. And so the solution curves sort of, since all getting pushed onto the same thing, they sort of cross each other here, right? This is many solution curves, not just one, and they all behave pretty much the same. But in the slope field, the solution curves can't cross each other. Okay, and so there's that analysis. For dy dt equals y sine y, let's see if I have space here. We can put the phase line in here. It's just y. We've got 2 pi, pi, 0, minus pi, minus 2 pi. Those are my equilibria. In between here, let's see, these are up, down, positive there, positive here, negative there, positive there, right? And that's the sign of the derivative. Y prime is negative, y prime is negative. So what does that tell us about this? Everything is running away from this, so this is a source. Everything is running into this one, so this is a sink. On one side, we're running away. On the other side, we're running to. That makes this a node. Minus pi, everything is running away from it, so this is a sink. And at 2 minus 2 pi, everything's running towards it. So that's a source. So the phase line is a little bit easier to see sometimes, whether it's a sink, a node, or a source. So that's what a phase line looks like. So here's another example. Suppose all you know about the right-hand side of this autonomous differential equation is that these are the only zeros of the right-hand side, and that the derivative is positive on these three intervals. So what are the possible phase lines? So one possible phase line, well, we'll just throw the information that we have. So the phase line is y. Got minus 10 is an equilibrium, because that's where the right-hand side is equal to 0. 5 is an equilibrium, and 7 is an equilibrium. And the additional data they tell you is f of y. Now remember that f of y is y prime, it's your derivative, on the intervals of y less than minus 10. So the derivative is positive down here. That means all my solutions have to be increasing. Between 5 and 7, the f of y is greater than 0. That means my solutions have to be increasing here. And for y greater than 7, f of y is positive. So they give you that. So that's the info. So what are the possible cases? Well, one is that the derivative could be negative in here, and you get that, which makes this a node, this a source, and this a sink. Case 2, right? The basic info again is 7, 5, and minus 10 are our equilibria. Positive here, positive here, positive here. The other case is that y prime is positive. Minus 10 less than y less than 5. What happens then? Well, everything is a node. Right? Because we're just going up, but we've got these equilibria. So two possibilities. Remember though that these are the only zeros. So we know that there's no more equilibria between minus 10 and 5, and that means the sign of the derivative, right, the y prime, that always has to be either positive or negative all the way through that interval. You don't have to worry about any other equilibrium. So what do the various solutions look like? Well, the information that we had from above is that our solutions are minus 10, 5, and 7 with the equilibria. So if you've got the phase line, how do you go about drawing the solutions? This is all the information we're given. So if y of 0 is minus 12, and we want to draw the solution curve, here's t, here's y, and we want y of 0 to be minus 12. Well, that's below this equilibrium at minus 10. So minus 10 is an equilibrium. And we know that the slope field here is always positive, right? So all our slopes here are positive. And so my solution curve going through here has to look like this. What about y of 3 equals 0? Well, we don't really, oh, y of 3 equals 0. We don't really know about that one yet. But we know y equals 5 is an equilibrium. We go 1, 2, 3. Y of 3 equals 0 is starting here. And there's one of two possibilities for this. One is that you could go up and down like that. The other one would be that you would go like that, depending on whether the sign here in between minus 10 and 5 is positive or negative. Y of minus 2 equals 5.5. that means starting at about here. And we know y equals 7 is the other equilibrium. And we know that the derivative is positive, right? Arrow up everywhere in here. So all my slopes are positive. So if I start there, I must have come from back here and climb up to here. And then y of 0 equals 7. That's just the equilibrium. And y of 0 equals 10. That means we're starting up here somewhere. And that means we go out like this. What can you say about the domains and ranges? Well, for this solution, for example, domain is minus infinity to we don't know, because we don't know whether or not there's a vertical asymptote out here. The range, your y values are always greater than 7, right? We've got a horizontal asymptote out here, but we're just going all up, up, up. For y equals 7, the domain is all numbers. The range is just exactly 7 because it's a horizontal line. If we look at things starting between 5 and 7, right, for a solution in here, the domain is all time, and the range is between 5 and 7, right? So if we start here, climb almost to 7, but never quite get there, and we'll climb back down almost to 5, but never quite get there. So autonomous differential equations have pretty strong, the behaviors of autonomous first order differential equations depend strongly on the equilibria. The solutions travel between equilibria, they go to plus or minus infinity, but we don't know what the domain is if it's a possibility that you actually do go to plus or minus infinity.